Fraud is a difficult and large-scale problem that impacts many businesses around the world. The engineers who toil away to prevent fraud are doing valuable and underrated work. As a payment processing platform, Stripe has to deal with many cases of fraud in its daily operations. Its fraud prevention product, Stripe Radar, operates at a massive scale, blocking billions of dollars in fraud for millions of businesses across hundreds of billions of transactions. This is an important financially consequential application of machine learning that doesn't get as much attention as other uses. My guest today, Ryan Drapeau, is one of Stripe's most senior ML experts and a technical lead for the payment fraud organization, where he has been instrumental in developing Stripe Radar. We spoke about evolutions in Stripe's ML architecture for fraud prevention, how to build and maintain ML systems in high-stakes situations, Stripe's approach to ML development, and much more. This is the Gradient Podcast, and I am your host, Daniel Bashir. If you enjoy these episodes, you can follow us wherever you're listening to this podcast episode. You can also follow us on Substack to get regular notifications whenever we release a new article, newsletter, or podcast episode. You can also find our online magazine at thegradient.pub, where we regularly publish essays by the sorts of people I interview on the podcast. And finally, if you enjoyed the episode, it would mean a great deal to us all if you'd consider leaving us a review on whatever podcast player you're using to listen to this episode. It helps more listeners like you find what we're doing and helps us bring in more interesting guests for you to listen to. But now, without further ado, Ryan Drapeau. Ryan, you currently lead Stripe's payment fraud organization as a staff software engineer. You have worked quite a bit on building some very important features for Stripe's fraud prevention. So I'd love to hear a little bit about your background and your route into machine learning.
Yeah, thanks for having me. My first interest in machine learning started in university as an undergrad. I became really interested in the wisdom of crowds problem and just that space. And so kind of the idea originated from, there was this county fair, I think in the early 1900s, where guests were asked to guess the weight of an ox, right? Kind of like each guest had one individual guess. And one of the people that was running this, Francis Galton, observed that the median of the crowd's guesses was closer to the actual weight of the ox than any individual guess. And it really showed this like collective intelligence is superior than any like individual's intelligence. And I was quite interested in this problem when it comes back to label quality and like data integrity with machine learning. Labels are almost everything when it comes to a machine learning model, in terms of like, you put garbage into a model, you're going to get garbage out. And so that was really my interest stemmed from this problem. And I did some undergraduate research working on wisdom of crowds problems, which then translated into some graduate research still in the crowdsourcing space. And when I looked for a job outside of university, the kind of data integrity problem was still at kind of like the forefront of what I wanted to work on. So I joined a ML team at Facebook where we were focused on content moderation and building ML systems to detect and prevent content that shouldn't be on the platform. And most of the labels from that space were crowdsourced labels or human labeled content. And when it comes to Stripe, which I joined after Facebook, I was really focused on this problem of fraud at this time. And the theme of my career so far was primarily data integrity and data quality. But there was a second one that started to become even more interesting for me in the space of machine learning, which is this adversarial nature of this domain. And the fact that I'm on one side of the table trying to build these machine learning defenses, and there is someone else or a group of people on the other side of this table that are trying to defeat everything that I'm doing. And that really came through in both the content moderation space in my time at Facebook, but even more so working on stopping payment fraud at Stripe.
The content moderation space, identifying hate speech, spam, dealing with disinformation, all of these areas do seem very importantly adversarial, and it's hard to conceptualize them as anything but a cat and mouse game. And so I guess I can kind of see that coming as a through line here. I'm curious for you, before we dive into fraud proper, you mentioned some of the top level differences between your work on content moderation, data quality, and then your work now on fraud. Can you maybe speak to a little bit more of the differences in the adversarial relationships that those two spaces admit themselves?
Yeah, there's probably like a lot of both similarities and differences between the spaces. Just in terms of similarities, spam and fraud are both financially motivated, right? So the attacker or the other person on the other side of the table is trying to generate money. That's what motivates them at the end of the day. And that's a very different motivation than when we're talking about some content like hate speech, right? Hate speech generally isn't something that generates lots of money, or at least it didn't when I worked on the problem in the past. And so I think when you add a financial incentive to this problem, it it becomes quite different in a sense. Like the fraudsters in this case, or spammers in content moderation, it is their full time job to make this money in this way that happens to go against either the platform rules or against the law in the case of payment fraud. And so just as much or as much time as I'm spending trying to build these defenses, there's someone who's spending an equal amount of time, if not more time, trying to defeat them. A fun example that we found, this was at Stripe, not necessarily at Facebook, but we were curious at like when fraud occurs, just like throughout the week. Like, do fraudsters live and work normal lives similar to what I try to do?
Is it a 9 to 5?
Is it a 9 to 5? Is it Monday through Friday? And somewhat unsurprisingly, it is, right? Like fraudsters generally are working normal working hours, and it's their job. And so I like to think that there's like an equivalent of me, but on a fraud team, some are trying to commit fraud, and they're probably using machine learning tools to do this, right? And so going back to the like content moderation space, or even the payment fraud space, like there's probably this rise of like LLM generated content that people are doing and they're using to try and best the defenses or systems that may not be ready or prepared for that type of like machine generated content at that scale. And so it's been quite interesting to see kind of like that journey and like how much in common there actually is between working on a content moderation system at a company like Facebook and then going to work on fraud defenses at a company like Stripe.
Yeah, it is interesting to think about it that way. Let's talk a little bit more about how fraud manifests as an issue for businesses, that top level question, before we dive into some of the technical details. So we have you, Ryan, working on fraud prevention. We have an anti-Ryan out somewhere who wants to make trouble for Stripe or another business. What does that look like, and how does that create problems for businesses in general, and then for you folks at Stripe?
Definitely. If Ryan and anti-Ryan ever meet in physical contact, like that's probably something bad will happen there. But so Stripe's mission at the end of the day, right, is let's grow the GDP of the internet. And the only way we're able to do that is if the businesses that use Stripe are also successful. And a business, if they're spending a large portion of their time dealing with fraud, and what I mean by dealing with fraud, right? Like when fraud occurs on your business, it's not something you just like get to ignore. So a fraudulent dispute comes in, you may be out physical goods, maybe you shipped them already, and so you're out of that money. You have some administrative work that now needs to be done to deal with the fraudulent dispute by kind of filling out a case report and sending it back to the bank, or in this case, Stripe. And that takes time. It takes people, it takes time away from running your business. And you could have spent that time growing your business in any number of ways, but instead you're kind of using it on this like just net loss of fraud. And so that's sort of like where Radar and Stripe come into play, where it's if we can minimize the amount of time any single merchant is spending managing and fighting fraud on their platform, and if we can do that job well, that means they can spend more time growing their business in a healthy way, which then achieves this overall mission of growing the internet's economy.
Let's spend a little bit more time on the problem here. I have a few different questions about it just so that folks can understand what it looks like a little bit more. So, one pretty clear thing is that there are many different types of fraud. Some listeners may unfortunately have experiences in their own lives. Hopefully not, but very, very likely. So, could you speak to a little bit about the range of types of fraud, perhaps how those look different in terms of the time tax or the monetary tax that imposes on businesses?
Yeah, let's walk through an example where maybe I'm a fraudster and I've stolen your credit card and kind of like what that might entail. So let's say sometime in the past you shopped online maybe with some merchant that wasn't using Stripe or using a top tier processor, and they were trying to do things on their own. They may have stored your credit card when you processed with them, the raw credit card details, and that is quite a large like vulnerability which exists, where like this merchant who's maybe not the most technically savvy has your credit card details in a txt file like hosted publicly. um, you know we laugh a little bit about this, but like this is real, and like this happens every day. And I, a fraudster, at some point, like realize this merchant has done this, and I steal this large TXT or CSV file of millions or thousands of credit cards and their details. And so the first thing I'm going to do as a fraudster is I need to filter this list. I have, say, 1 million credit card details over the spanning the last like 10 years this merchant has been in business. And I need to understand which of these credit cards are still active and the information associated with them, is that still correct? And so we call this in the space card testing, and it's the first kind of phase of fraud. And so, as the name implies, we need to test these card details for their validity. And I can target processors like Stripe or other processors in order to try and extract this value, where essentially I will, enumerate these card details on payments that I don't really care if the payment succeeds or not. All I care about is this card good or not? Because what I can do at that point, once I have a say golden set of these cards, is I can resell them. I can go on the internet and sell them to someone else who wants to commit the actual fraud of extracting value. And we would call that second phase card caching. And so that is kind of what I think most people think about when they think about credit card fraud or fraudulent disputes, is when I now, I bought this golden set of cards and I go to some merchant and I pick the fastest shipping speed and I use the fake credit card details and I try to get the physical good before they find out that it was fraudulent. And that card caching is essentially like you're caching the card for some value and extracting it. And so if you're a merchant in all of this, both of these types of fraud impact you quite greatly if there's no defense in place to try and stop it. So the kind of like card networks or just the ecosystem of online payments, they don't like this fraud. Obviously, there's like rules in place for how much fraud you're allowed to have on your merchant or any individual account. And if you start getting close to what they deem as the threshold, uh, you could get in trouble. It means like higher processing fees for you. You're spending more time responding to these inquiries and or writing reports for these fraudulent disputes. And in very egregious cases where there's just no defenses against fraud, like they could stop processing for your business. And that essentially means you're dead in the water as a merchant in this case, where you didn't have any fraud solution in place. You got hit with massive fraud attacks and you weren't able to stop it. And now you can't process credit cards anymore.
So, of course, this looks really bad for the people suffering from fraud attacks. You described how and there are sort of different ways to extract value from types of fraud. So we have card caching, we have the people who actually want to use the cards, and this does kind of manifest as an industry. I guess you could think of it a little bit like ours, right? People working 9 to 5 jobs, making money off of this. Could you describe that in a little bit more detail, just what fraud looks like as an industry on that side?
It's it's funny. I've always wanted to learn more about the anti Ryan on the other side of the table here, and we've looked at like websites. Like there's almost like SaaS businesses for committing fraud out there. And they don't last long because they eventually get taken down either by the FBI or like other entities. But like some I've seen, like this card testing problem, right, where you're trying to test cards. There may be another player in this which is the person who offers the card testing service. So there could be a player who has a set of credit card details and they want to understand whether they're active. And they may go to a service that offers these card testing capabilities, pay them a smaller amount of money, and that service will then be the one that tries to understand or extract the value, which is this card active or not, kind of like a cleaner service. And then the person who used that service, then can take that like golden set and sell it, excuse me, again. And I think like that's just a really interesting kind of like business model that exists in this space, where like those people are a software company at heart, right? Like they're building scripts, they're building tools, they're building automation to automate these checkout flows and or interfaces with processors to try and understand, like, is this card active or not. And what they're dealing with as they do this is all the fraud defenses that may exist on the platform that they're using to determine if the card is good or not. And so that's kind of where like Stripe Radar really comes into play, which is if you chose Stripe or a merchant that uses Stripe to try and test these cards, well, then you have to deal with me and then all my team's work to try and get past our defenses to get that value at the end of the day that you're looking for. And that may be quite a bit more expensive than going to another merchant or someone else who's not using Stripe. And so there's this other kind of like, I imagine, research arm of this card testing company that is trying to understand various vulnerabilities in various card processors online, where they're trying to figure out where the weakest link is and kind of hit that harder than they otherwise would because they'll get more value that way.
Do you find at all, or would you conceptualize that there's anything of an information asymmetry between you trying to defend against fraud and folks who are committing it? I would imagine by nature that a lot of the fraud industry, it probably takes some digging to get information that you might want to find about them. Now, of course, Stripe's vulnerabilities aren't necessarily exposed, but perhaps the architecture of different systems or things on Stripe blog posts, those could potentially be some kind of useful information for a potential attacker. And so I guess I'm curious how you think about that information.
Totally. I mean, this podcast is a good example of information that might be useful for a fraudster, right? So,
Hmm.
hello, any fraudster that is listening. Um, I think there's definitely information asymmetry between the attackers and defenders here. I think to the same extent that fraudsters are kind of on the hunt for finding vulnerabilities, we also are looking to do that internally. But the power that Stripe really has here is we get to see everything that happens across the Stripe network. You as a fraudster are, I would imagine, more weary of sharing your information with other fraudsters. Like those are essentially your competitors in this space. Like if you imagine there's like two card testing services that exist, like do they really want to share their knowledge of vulnerabilities with one another? I'm sure it does happen. Like there is kind of like a bragging rights nature that I've seen to like some of these fraudsters, and there's like clout of like if I share an exploit that's really good, then I get a lot of good reputation as a fraudster. But at the end of the day, like at Stripe, we see all the activity that happens across our network, every single merchant and all the payments that are crossing them kind of builds this aggregate knowledge and wisdom of crowds. If you want to throw it back to my background, like we can build up this view and model of like what fraud is and what fraud isn't, and use that to apply a more thorough defense than if we were operating at, say, an individual merchant level. And what I mean by that is like, imagine I was just at, some random merchant. Let's say we're like a medium-sized merchant, and it's my job to stop fraud from happening on our business. I'm limited in some sense to the information and the payments that we process at that merchant level. And building a machine learning system in that case is going to be quite difficult. Like we may not even have enough data to train a sufficient model to act as a defense to block bad customers, but allow good customers. But at Stripe, like again, like we have this data, this network that's been built up across millions of merchants and billions of payments, where there's enough data there that makes it like ripe for these like machine learning defenses, which gives us a pretty large advantage against these fraudsters that they don't have.
This is a good segue then into how you've begun leveraging ML at Stripe in order to deal with the fraud problem. So you described how this is sort of a challenge that can be tackled with ML. And it is, I guess, a problem where maybe there are some difficulties in working with the data, the comparative rareness of fraud. Could you describe a little bit more how you start to formulate this as an ML problem? And then we can maybe start working our way towards understanding Stripe radar a little bit better.
Yeah. So a payment comes into kind of Stripe and Stripe's API, right? And there's some characteristics of that payment that we just get by the nature of payments. So that's information like the amount, the card number, the email address. If there's a shipping address, like we'll see that too. And so imagine all these like high level signals that describe this payment are available at the start. And what happens is within around a couple hundred or order a couple hundred milliseconds, that payment is going to go to the payment network. So that's like the issuing bank that owns the credit card. And in that time, we can make a decision of whether we want to allow that payment or block that payment. So that's kind of our action space and at the point in time in which we would take that action. And that's the first part of the machine learning lifecycle. It's like, here's our input signals, here's the point at which we would take the action, and then the label comes from the bank, or in reality, it's really the end customer, the person who owns the card. You review your credit card statement. Some people are diligent and do this every day. Other people maybe read their statement once a month, and you noticed, hey, that payment I never made that payment. So you call up your bank or you somehow submit and say, like, that's fraud. That makes its way back to Stripe as what we call a fraudulent dispute. And that ultimately becomes the label in this machine learning problem. So we have the set of good payments, which are the payments that don't get any disputes and aren't fraud as far as we can tell. And then there's the set of payments which are fraud, which were reported by these end customers. And so you put that all together, you have the input signals, you have the point in time in which you take the action, and then you have the labels. That's the setup that's needed to start using ML or creating an ML feedback loop or cycle, which is what Stripe Radar does.
Great. So we have the basic setup of this problem. So we have our input, that's a payment, card information. That goes through the Stripe API to the payment network, and we want to make some decision of whether we're going to allow or block it. We might be looking for similarities to patterns of transactions that might have triggered a fraudulent dispute in the past or something of the sort. Could you describe a little bit then about how the system that actually ingests this data, figures out how to make these decisions, how it has evolved over time to where it is today?
Yeah. So if we zoom back to around 2013, the first iteration of Stripe Radar was created here. And I'm fairly sure it was a logistic regression model at the end of the day. So, start simple, move fast was the mentality back then. And what we have to do first is we take those input signals that I mentioned. So like the email address, the card, etc. We call those signals, and we need to transform them into features for our model. And so back then, there were some rather bespoke and handcrafted systems that were created to do that. And so some examples of features might be, what are the number of unique card numbers associated with an email address? Or when was the first time, or how long has it been since the first time we saw this email address on the Stripe network? How about since we saw it used on this merchant before? And so you can imagine there's hundreds of these features that were built up over time. And they were all kind of like manually implemented and managed in kind of this like bespoke Redis and or Mongo system that we had. And we realized that didn't scale around 2016, 2017. What we were facing was this problem of, I refer to it in machine learning as like log and wait, which is I create a new feature, like that unique card number feature I mentioned, and I implement it, and now I'll get that data going forward from this point in time. But I have to wait, let's say 5 to 6 months in order for enough payments and fraudulent disputes to accumulate with that new feature before I'll have enough to retrain my model to incorporate it. And so this is a problem that in some sense was unique to Stripe, in that fraud is quite rare. We look at generally 1 in 1,000 or even less payments on Stripe are fraud, and because of that, it takes quite a long time in order for us to accumulate enough data to be able to train these machine learning models. And so this log and wait approach is quite detrimental to iteration velocity, right? Like anytime you have a new idea for a feature that you want to add, imagine you'd have to wait essentially 7+ months before you could even understand the impact of that new feature. And so we tried a few techniques to get around this over the years. And like, the most natural one is like, we'll just backfill the feature, right? Backfill that new feature you've added and compute it over your payments data for the last year. And the main challenge with doing that is time travel and label leakage. It's very easy to leak the future back into the past, which then when you incorporate into your model, and ship your model to production and have it predict current payments, that distribution is going to be different. And so your model learned a behavior of like having knowledge from the future, which now it's not going to have at prediction time. And so the main evolution of, I would say, our ML systems came when we solved this problem of we want to be able to implement features quickly, but we need a way to be able to backfill them safely with these like time travel guarantees where we're never looking into the future. And the nature of the system is one of it's essentially everything is built on events. And what I mean by that is, so like we'll take that payment that comes into Stripe and those input signals, and we'll construct an event that has a timestamp. And that becomes our canonical representation of what the payment is. And we can send that event to the system to be processed to get the features for it, but then we also archive the event. And so anytime we create a new feature and we need to recompute or compute the value of it across payments that happened in the past, we can essentially just replay the events of all the payments that happened to get a accurate point in time value of that feature, which is representative of only the events that happened before it. So in practice, this is a Lambda architecture that we've built internally at Stripe for doing this type of feature computation. And it's what powers our models today.
So I guess starting from here then, so at the very beginning, we started with pretty simple ML architectures. You solved this backfilling features problem, which is pretty important. And now we're maybe at a stage where we'd like to see what further improvements we can make. So I think you identified a number of different things that went on. And so perhaps could you speak a little bit to the evolutions in the actual architectures that you were using, how those were motivated, and then perhaps some of the improvements that you saw afterwards?
Definitely. We like to view this as there's two main levers to improving our ML or fraud defenses. There's improving the features themselves. So that's adding, new signals or new types of data into the model. And then the second is, to your question, like the evolution of the architecture of the model itself and how that changes over time. And so I mentioned earlier, logistic regression was our, starting point in 2013. And we've come a long ways since then, and kind of these like more classical machine learning methods. I think our journey was not unlike many other kind of companies in the ML space over this time period. So we start with logistic regression. We move to random forest or some tree-based approach, and then settling on XGBoost, which was kind of like the best of the, let's call it like classical machine learning methods. And XGBoost does quite a good job at handling the types of data that we're dealing with in terms of these features, right? We're not necessarily in a text domain or an image domain or a video domain, like previous role at like content moderation. Like this is really like tabular data and hand engineered features which are powering this system. And so something like XGBoost was quite performant at being able to do this job well, and served us for many years. I think the first XGBoost model we started in 2018, and we didn't fully get rid of our dependency on XGBoost for this model until last summer, so summer of 2022. But throughout that time, there was quite a few interesting stories of kind of attempts to move beyond this like XGBoost model that was like really quite good at detecting fraud. So I joined the company in early 2019, and my first task was to build a recurrent neural network with the idea that payments are essentially like a sequence, right? Like we have multiple payments that have occurred on like a card, for example. And so that is a sequence that we can transform into a representation that would be best suited for this like state-of-the-art approach that was really gaining a lot of traction at the time, which is these like sequence-based models. And I failed at that, of course, otherwise we wouldn't have used XGBoost till last summer. And really the problem came with XGBoost as a baseline. Like it necessarily wasn't that we're trying to build a recurrent neural network or a sequence-based model that works, right? We'd need to build one that's better than the current production model. And doing that at scale was quite challenging. We, at the time, like had trouble scaling up these recurrent neural networks beyond to be able to match like the number of events in a sequence that would be necessary to beat XGBoost. And so what I mean by that is like there are multiple different sequences in the payment space that matter in the context of a single transaction. So we have these signals, card number, for example. There's a history of transactions that have occurred on that card number. There's also an email address present. There's a sequence of history of transactions that have occurred on that email address. Same with IP address, etc. Like there's all these various sequences that exist. And our current model on XGBoost has some knowledge or context of all of those because it has features present that are aggregating across all those different dimensions. And so when we build a new sequence model or new recurrent network and its only input is the sequence of history on a card, well, it's at a huge disadvantage compared to XGBoost, which has this aggregate knowledge across many more dimensions. And that scalability problem is one we still face today as we try to explore other architectures like transformers or other sequences, and has been the main motivator for why we were staying on XGBoost initially. We pivoted this project from RNNs to then be just a traditional deep neural network model, kind of like starting a bit easier than trying to go straight to RNN. And that was almost good enough. So we did what any machine learning practitioner does, and we just ensembled the two models together and we get something that works better. So we called that, inspired by some papers out there, called wide and deep, with the idea that we have a wide model like XGBoost, and we ensemble that together with a deep model like this deep neural network, which is traditional DNN. And that was what kept us going until last summer. And at that point, we were looking to make another evolution of our architecture to really drop the XGBoost component. And I think the motivation is beyond just like, yeah, we want to be able to say we want to use deep neural networks and only deep neural networks. It was really that like we were facing scaling limitations with XGBoost now. And so, between 2019 and 2022, like Stripe's data grew quite considerably and over several orders of magnitude. And that gives us several orders of magnitude more data to use. And what we found was it was quite hard to just throw more data at this problem, like expand our training window, give it more training samples with XGBoost. And we were looking at like training times for our model on the order of like 15 to 20 hours to train the production model. And it was largely dominated by XGBoost here. So there became a really strong desire to speed up our iteration time by removing this component, the XGBoost component, and landing on what we'll call like a pure or DNN only type architecture. To kind of summarize like the architecture we did land on, we had a PhD intern join our team, and she was quite interested in residual networks and this paper ResNets that had come out, and was like, well, let's just try it. She's here for 12 weeks. It seems like a great intern project to try. And it turns out it worked quite well for our problem. These like residual networks plus doing quite a bit of hyperparameter optimization on top of that, we ended up with a model that was quite a bit more performant than the wide and deep model that we were coming from. But even more importantly than the performance, in my opinion, were kind of like two major pieces of impact. The first was the iteration speed. We went from 12, 15 plus hours now to order 2 to 3 hours to train the model end to end. Having that reduction from 12 to 15, or from 15 to 12 to around 3 may not sound like a ton, like it's still 3 hours of time, but now you're within one business day for iterations. So when an ML engineer conducts an experiment, like they can get their results that same day, and there's less context switching between that day and before, when they had to wait till the next business day to even work on it. And so that was quite a large capability gain or shift. And then the second was dropping XGBoost sets us up for a lot of more explorations into state-of-the-art machine learning techniques, right? There's, as great as XGBoost and like these tree-based models are, like the industry as a whole, and especially like the research side of the industry, is primarily focused on deep neural networks. And that's where all the improvements that we're now looking at have stemmed from. So examples would be like transfer learning and trying to do like that within the payment front space, or multi-head attention, or et cetera. Like if you read any recent research paper, this is where we're going to get our ideas for how to further improve our architecture now that we're on a simple deep neural network.
That makes sense. Do you think there were any, I guess, part of the motivation for using ResNets in particular, it sounds like you happened to have a PhD intern who was interested in that suite of models. Do you feel there was anything about the particular ResNet architecture that maybe made it well suited for this problem? Or was it more just like, we tried this, it happened to work?
I think so her background was all on like neuron explainability and deep neural network explainability. And so I think she had recently looked at that particular architecture as being more explainable than other state-of-the-art DNNs. And so one of the kind of important aspects that we think about with our machine learning models is how explainable they are to our merchants. And so an example is like we display our score or our evaluation of risk to merchants at the end of the day. And the most natural question anyone would have is like, well, why did it score this way? And when you're using logistic regression or tree-based models, it's quite easy to answer, right? You just like peer under the hood into the model and you're like, oh yeah, this is the weight for that feature. This is why this feature contributed the most to this score. And with deep neural networks, it's a bit harder, right? Like that's kind of where state-of-the-art research really is at right now. And so like you can use tools like SHAP and extract like Shapley values for trying to explain your model's decision and what features contributed the most to it. And so I think it was a like, hey, this architecture seems cool. It has some benefits that are related to this person's research and what they were working on, and we tried it and it worked. So I think that summarizes where we're at now. I think it's important to remember though that like we don't want to get too comfortable with being solely on this architecture. I think it would be a failure if we did not evolve past like ResNext and to the whatever is going to come next on a faster timeline compared to like how long we were using XGBoost.
As you think about the future architectures you might want to develop towards, one pretty clear issue that you have mentioned that many people are aware of is the trade-off between model performance and explainability. And you did capture in your blog post on Stripe Radar that, and here as well, that to you explanation matters as much as detection and performance, because ultimately when you make a decision to block a transaction, we think this is fraud. That's something you are going to have to explain to somebody. They'd like to know why it was declined. They'd like to know if that indeed wasn't fraud, what they can do to make sure that it isn't detected as fraud the next time. And so, as you think about evolving your architectures further, have you put any thought into just where what you'll need to do, I suppose, in order to maintain that aspect of things, in order to still be able to explain to customers?
Yes, I think as you mentioned, like it's as important that as much as we improve our performance of our models, that these decisions that these models make are explainable to our customers. Just to paint the picture here, like if you're a business and Stripe Radar starts blocking, say, 5 to 10% of your transactions, which would be quite a lot, you're going to want to know why, right? Like that could, in your mind, be good revenue that you're missing and not a fraud attack that you're currently under. And so being able to explain to a merchant that Radar is making these decisions because you may be under a fraud attack, and here are some key signals that went into the evaluation, are it's critical that we get this right. And so I think of it less as a model architecture problem. So I think as we improve or evolve our model architecture, like there will be tools and state of the art tools that we have where we can peer under the hood of the model and try to understand its decisions. Right now, we primarily focus on Shapley values and using those, and that has worked well internally. And what I actually think is this is almost like a user experience and merchant, or like a problem that we have to solve using tools we make accessible to the merchant. And so an example of this would be if we tell the merchant that, hey, we blocked this payment because there were a lot of declines on the IP address that was used to make this payment. We ought to give that customer and that merchant control so that they can tune to their business how sensitive they want our decisions to be to that feature. And the way we do that is another component of Radar, which we didn't really dive into in this talk, is there's a whole rule-based component to this where you as a merchant can customize and write rules for your business to essentially act as like one more lever or one level deeper of control that you have access to. And you could imagine the way this would work is like if you're that business with this, Radar is blocking 5 to 10% of your payments, and like this is not fraud, and you see that Radar is blocking it because of these signals or features that are on the IP address, and maybe this is because the payments are all coming from one location, but you're confident that that's not fraud. Well, you can go in and write a rule to help customize or augment the ML performance. And so, in some sense, this is kind of like human in the loop machine learning and like tuning for per merchant outcomes that you're looking for, where giving merchants the control and giving them levers and actions is just as important as the explainability and just as important as the performance of the model, because ultimately like some merchants will want to take a little more control because they believe they can extract even more value out of the system than what it provides kind of by default.
We've spoken to, I think, a lot of the particularities, the architectural concerns, the nature of what fraud looks like for businesses and you at Stripe having to deal with it. I think from a high level with the use of some examples. I guess I'd love to hear a little bit more about some of your on the ground stories, about some of the more tricky things that you and businesses that Stripe serves have had to deal with.
Yeah, the one I would point to the most is this idea of data locality. And what that means is that there are many countries, states, and or legislatures out there in the world that are passing laws that limit where data can be stored for the citizens or users or businesses within that domain. And we talked a lot about on this call so far around the importance and the power of the like Stripe network and the breadth of the data that we have available. And data locality makes this a little bit harder as it fragments that network. And what I mean is, like, imagine you're a fraudster and you're committing fraud in, country A, and you go and commit fraud in country B, but country B has a data locality law that says nothing from country A can come into country B. That means if we didn't do any additional techniques, when we make the prediction or evaluation of your payment in that second country, we have no knowledge of the previous fraudulent activity that you committed in country A. And this essentially poses like an existential risk to fraud systems, that if you do not account for this fragmentation effect in your features or in the signals that are coming into your model, then you will essentially fly blind when you're making predictions, and fraudsters will know that and kind of try to abuse that hole. And so we've had to explore quite a few techniques to get around this. And one of them is essentially this idea that we can take a payment and pass it through an encoder and create an embedding for that payment. And that embedding now may not be subject to the data locality legislature, because it's no longer a payment. It's no longer any data that would be usable or identifiable, like personally identifiable information. And we can take that and kind of bypass these data locality laws, or kind of extract the data to a level where it no longer matters or it doesn't apply. And we use that to expand or keep our network kind of as stitched together as possible. Other techniques is like you could just try to give some signal that this fraud attack happened in this country to another country. And by transferring that information, itself is not subject to data locality, but just the knowledge that like this card was used, and you can do that via something like a Bloom filter, would be useful for making predictions within the more restrictive locality zone.
I guess another kind of aspect of this I'm curious about too, really the locality constraints, as I understand it, are sort of coming from different countries, and they have more restrictive laws or regulations over the use of data. And so that really impedes what you can do with it. I do understand there are, and I'm not an expert on like federated learning or anything, but I know there are techniques like that that are supposed to allow you to still aggregate data while respecting data privacy. Are those sorts of techniques things that you're able to think about using in this domain, or am I kind of barking up the wrong tree with that question?
No, that's spot on. I think the embedding approach I described earlier is like a more naive approach, or kind of like a first stepping stone on this way to doing full federated learning. And it's an active area that we're still working on, and also, paying close attention to how these data locality laws are going to evolve so that we can plan the evolution of our own systems. You might imagine like it's only advantageous for us to do this if we know that data locality laws are going to fragment our networks in a certain way. And that's just like us getting ahead of the game. And we're kind of like, paying very close attention to current legislature out there to see if that's actually going to happen. I think the important distinction that I'd add, like federated learning is quite a broad word or term in terms of what it describes. But I think people, when they think of like these data locality laws, they immediately think like, oh, like this is going to impact your model training. Like your model can only train on data from country A or country B, and that is itself going to be detrimental to its performance. And that is true. I think even more important is the network signals and features themselves, or where we see more of our performance degrading when these laws come into effect. So just the knowledge that, hey, this card was used in country A and country B requires you to pass data across these data locality zones, which may or may not be allowed. And if you're not, like, if you can't share that data, then when your model is making a prediction, it doesn't have the context of the history of this payment, and it can't make as accurate of a decision. So like regardless of your model architecture and like, or your model and how it was trained and what data it was used to train, if it doesn't have the context when it makes the prediction, then you're going to lose performance.
Yeah, that makes a lot of sense. You've described a couple of different vectors for improvement on current fraud detection systems. So you have the further evolution of architecture. We have what we've just described. Are there better ways to train our models while respecting data locality constraints? Of course, there's the evolution of kind of understanding features and the nature of fraud. Are there any other directions that you think about as potential ways that these systems could be improved?
It may be a rehash of what you said, but like additionally, there's beyond model architecture improvements, there may be just tweaks to the model training process itself, kind of coming back to data integrity and like garbage in, garbage out. Like if the labels themselves of whether a payment was fraudulent or not are not accurate, then your model itself and its performance will not reach its true potential. And I think this is one of the exciting things I was most looking forward to when I came to Stripe from content moderation, was this idea that labels were almost always true. Like we could take them at face value. Like the issuing banks or card holders themselves are good actors. And when they file a fraudulent dispute that like, hey, this was fraud, I didn't make this payment, that would always be the case, and like the label quality was at 100%, and that just turned out to be so incorrect and false, or it was just a wrong assumption that I had coming in, and actually like a lot of the team had, until we kicked off kind of a research project to look into label quality specifically. Everyone assumed that it was good, but it turns out not all people are good actors. And there's this concept of, we call it mislabeled fraud internally, but this idea in the industry of friendly fraud, which is that you yourself are a fraudster, but you're going to make a payment with your own credit card and then claim you didn't make that payment. That is a very different machine learning problem to tackle, because you can imagine our systems up until this point have all been focused at trying to detect when someone else is using the credit card that isn't authorized to make the payment. So, differences in IP address or changes in signals that we could detect. This is a very different case where it's the same person. So, like, all those defenses that we've built now need to adapt to this new approach, which is, hey, this person is making the payment. They've made all the previous payments on this credit card, but they're going to dispute this as fraudulent. And I think that's the next big jump in kind of our perceived model performance, comes from us really cracking this problem of how do we solve this label quality issue at the end of the day, and train maybe two models, or add more signals to try and differentiate those two different behaviors.
I can see that posing a really interesting set of problems. I guess you would imagine that I go back and claim that I didn't make a payment on my credit card that I actually did. then we encounter the space of brittleness. Even if a bunch of other features look the same, something might fall apart. But it's probably even more likely that the features you have available to look at when I am a fraudster trying to call out on my own transaction, the whole suite of features, things that you have to look at, are probably going to look very different under what you capture, right? So I imagine that maybe you have to start thinking about a whole different set of features, or maybe there's incremental things you can change. But it does seem like there's a lot of ground up work there as well.
It it doesn't have to be entirely different. So you could imagine this is how we approach this problem, but like you could imagine looking at these fraudulent disputes, and there's other types of disputes that come in as well, like product not received or the product was damaged that aren't fraud. And you could actually train a model that tries to predict the dispute label or like the dispute class, the type of dispute that comes in. And we can use that to try and tease apart the fraudulent disputes that are originating from people that actually had their card stolen and fraud committed on their on their card, or and differentiate that from people who are just disputing fraud on their own card to try and extract some value, because the features and the values themselves, we will essentially with this multi-class model predict a different dispute label than fraudulent dispute for it. So the problem becomes not what is the likelihood of whether this payment is fraudulent given it's a payment. It's what is the likelihood that this payment is fraudulent given that it is disputed. And so the prior changes, and that alone is enough to start teasing apart the distributions to get some sense, or at least a high level understanding of how fragmented that space is.
That's interesting. And so, I guess in one sense, this problem initially might feel a little bit harder. Fraudulent, given it's disputed, you're in a multi class classification problem. So, on the surface, it's like, well, maybe we have a more complicated distribution to work out. But given the prior that it's disputed, that does give you quite a bit more information to narrow down on precisely what you're looking for. And so, in the realm of just is this fraudulent given that it is a payment, you do have that big data imbalance problem you were working with, where maybe in the multi class setting that's mitigated, maybe not to like a uniform distribution, but at least mitigated quite a bit. And so I guess I see how this can actually be a pretty interesting vector of attack.
Yeah, exactly. And then you can imagine, like, now that you have that multi-class model, you can use it to then filter the training set of your other model that's trying to evaluate just payments for fraudulent risk, to be able to fine tune it specifically in one direction or the other. You can, imagine having two models, that one does the friendly fraud prediction and the other does the more traditional just payment fraudulent dispute prediction.
I think this is a good place for a closing question. And so you spent quite a while working on Stripe Radar in the land of problems like content moderation, like fraud, these things that are ultimately adversarial. And these are, I guess, really difficult spaces to work in. Can you speak to, I suppose, the lessons you've picked up having had to engineer ML powered systems to both, I guess, what you've taken away both in dealing with these particular problems, but then in also building those systems more broadly?
I think the overarching theme is don't get comfortable. If you're working in an adversarial space, there are people who are going to continuously try to best your defenses. And if you kind of get comfortable and feel like you've solved the problem, so to speak, like someone will almost certainly prove that you haven't. And there's always room for improvement. And we view improvement across the two main levers internally within our ML teams, right? The building new signals and features for our models, and then also tweaking the model architectures or the training process such that they get better. And between those two, we see this kind of like continued evolution and increases in performance year over year of our machine learning. And we're going to continue to do that in the future. We have to, to achieve Stripe's mission overall of growing the GDP of the internet. The only way we can do that is if we can mitigate and minimize the amount of fraud that merchants are facing. And machine learning has a core role in doing that, as it's the main way to kind of like scale up your defenses and take advantage of this breadth of data that we have at Stripe.
That is a great takeaway, a very appropriate one too, and I think a great place to end. Ryan, thank you for taking the time to speak with me today. It was really interesting to hear about your work on Radar. I'm very excited to see what more comes, or I guess not having to think about fraud if I ever become a Stripe user or anybody I know ever becomes a Stripe user. So thank you for the work you're doing and for speaking with me today.
Thank you for having me.
And that is a wrap, my friends. As I mentioned at the start of the episode, you can subscribe to The Gradient on Substack to receive not just this podcast, but also our articles and newsletters directly to your email. You can also visit us at thegradient.pub, where you'll find all of that, as well as more information about The Gradient and how you could even contribute if you're interested. And finally, if you enjoyed this episode, we would really appreciate your feedback. If you'd like to leave a comment or review, we'd love to know how we can make this series more interesting and informative to you. And with all that, I'll leave you until the next episode.